So please don't be late. All right. So please try to hand it in before by noon on Tuesday next week. How are you guys? You had a good weekend? Yes? I've got some chocolates for you. You love chocolate? Yeah. These are small ones. Alright guys. Alright, so you have any questions on the stuff you did last week? Any questions you guys have on what we did last week? No? Yes? Come on guys. So this is okay. Just to summarize what we did last week, or what we did on Tuesday last week. I talked about the extremal types theorem, and then gave you conditions for the three types to hold. So if this condition is satisfied, then the limit will be Gumbel. And if this condition is satisfied, the limit will be Frechet. And if this condition is satisfied, then the limit will be Weibull. Okay? Okay, guys? So this is stuff we did last week. So sorry. Can you see this? Okay. This is stuff we did last week. Then I did one example. This is the example where the f is the CDF of the exponential distribution. And this example 2, f is the CDF of the Pareto distribution. Okay, that's example 2. And example 3 is the uniform. F is the CDF of the uniform distribution on the interval 0 to 1. All right, that's example 3. Now, example 4. Example 4 is this one here, where f is the CDF of, this is known as the exponentiated exponential distribution. right? We did this last week. And then I gave you alternative conditions. So these are conditions which are equivalent to the conditions I gave you earlier, but these three conditions are different from the earlier conditions. So if this condition is satisfied, the limit will be Gumbel. If this is satisfied, the limit will be Fresher, and if this is satisfied, the limit will be Weibull. All right. So, but you should get the same answer, right? Either using these conditions or the conditions that I gave you earlier, the answer must be the same, right? You should get different answers, then that means you are doing something wrong. Okay? Okay? All right. Then I did just one example on the alternative conditions, right? So I want to do just a few more examples today. Okay, so let me start by doing some more examples. All right, guys. So this is example 1. Example 2. Can you see this, guys? I don't know whether you can see this. Let me see. Can you see it from there? Oh, example 1, yeah. Example 1 will say. Okay, so example 2. Okay, this is example 2, right? And we know that for this distribution x, we know that WF is infinity, all right? And we know the density is the derivative of this, which is 1 divided by x squared, right? So I'm using the alternative conditions, guys. So you need to work out the density, and then you need to work out AFT. To work out AFT, you need to set f of x equal to 1 minus 1 over t. So this implies 1 minus 1 over x is equal to 1 minus 1 over t, which implies that x is equal to t. So this implies that A of t is equal to t. Okay? You follow me so far? Yes? Okay. Now B of t, what is the definition of B of t? Can somebody remember? What's the definition? How do we define B of t, guys?
T f of a t.
No, guys. It's t times f of a t. So it's t times f of a t, which is 1 over a t squared, right? So B of t will be 1 over t. All right? Is that right? Okay. Now let's check condition 1. For condition 1 to hold, the limit of btx divided by bt as t goes to infinity must be 1. All right? But this guy, btx, is btx will be 1 over tx divided by 1 over t, which is equal to 1 over x. which is not equal to 1. Alright, so condition 1 fails. Alright, you guys with me? Now condition 2 is, now let's try to remember what condition 2 is. You guys have better memory, I'm an old man. Condition 2 is that this W of f is infinity and the limit of at bt equal to alpha. Alright, so W of f is infinity, we know that. So okay, that is satisfied. Right? Now the limit of at times bt as t goes to infinity is equal to, it's the limit of as t goes to infinity of t times 1 over t, right, which is 1. Alright, so your alpha is 1. Alright, so hence alright, so the limit will in this case will be pressure, as we know. We already know the answer because we did this example before using the original conditions, right? Okay, yeah. Alright guys, any questions on this, guys? You guys okay? Yes? Okay, alright, so that's example 2. Example 3. Example 3 is where the CDF is the uniform variable, and we know that W of f in this case is 1, right? So f of x is the derivative of this, which is 1. Now to find a of t, you need to set the CDF equal to 1 over t, which implies that x equal to 1 minus 1 over t. So this implies that at is equal to this. Okay. Right, now b of t is t times f of at, which is, remember, f is 1, so it's going to be 1. So b of t is t. Alright, are you with me? So we determined the density, we determined a of t, and we've determined b of t. Alright, now we can check the conditions, starting with 1. So this is the limit Alright, okay, so condition 1 fails. Alright, because the limit is not equal to 1. The limit must be equal to 1 for the condition 1 to hold. Okay, now condition 2 also fails. because for condition 2 to be satisfied, W of f must be infinity, and in this case W of f is 1, so it cannot be satisfied. Alright, so condition 3. Now let's check what condition 3 is. Condition 3 is this one here, guys. Can you see this one? Okay, this is condition 3. Alright, so for condition 3, we know that W of f is 1, which is finite, so it is satisfied, and the limit of W of f minus AT is this guy here, multiplied by bt, which is t, right? As t goes to infinity, this is clearly equal to 1. You can see that, right? So the limit is 1. Alright, so hence condition 3 holds. Right? It's easy, right? Are you guys okay so far? Let me know if you have any questions, guys. Okay, so it's here. The next one is example 4. Right, this is example 4. The first thing we need to work out is the derivative. So we know that W of f is infinity. The derivative, little f of x, is the derivative of this, which is going to be a Okay, so this is the derivative. Okay, guys. Now the next thing we need to find is a of t. Sorry. To find a of t, we need to set f of x equal to this and solve for x in terms of t. So this implies that Alright, this implies this, right? So your a of t, your a of t this is your a of t. Now to find b of t, you need to just put t times f. F is this kind of complicated. Like this. Alright, so now if you work this out, this is where things get nasty. You will get, let me think, minus, okay, you get that. Then I'm gonna do this a little bit quickly. I hope you don't mind if I hope you don't mind if I don't show you all the steps. Just because if I show you all the steps, it might take a long time. So after simplification, you should put in the formula for F t into this one and into this one. After some simplification, which I haven't shown you, right? I'm sure you can figure out. Yeah. After some simplification, this is what you should get. I think. Correct me if I'm wrong. Okay. Okay. So that's your BFT. All right. Now let's check condition 1. Condition 1 says, according to condition 1, the limit right, this must be 1. All right, so let's see if it is 1. I need to go to the next page because I can't finish everything. So this is the limit as t goes to infinity of the following, which is a tx okay, this is what you get. Alright guys, alright, now okay, let me ask you now, let me put this here. Let me ask you now, what is, I know you guys are experts in calculus. As t goes to infinity, what has happened to this term?
0.
This goes to 0. And this one? Same. Right? And at will cancel with at. Right? So what you have is the following. You have this is what you have, right? Okay guys, now I told you something last week. I don't know whether you guys remember. I gave you an identity last week that if you have something like this, power a, right? This is the same as 1 minus a times z as z approaches 0. Do you guys remember that I mentioned this? I mentioned this last week, right? Okay, because as you can see, this guy here and this guy here, both of them approach 0, right? Both of them approach 0, so we can apply this result, right? Okay, guys, so what you have is the following. You have alright, the 1 and the 1 cancel, right? So you get this is equal to x times 1 over x, right, which is equal to 1, right? Hence condition 1 holds, right? You see, I know this is a long way to do it, so that's why, you know, it's important. That's why it's important. Sometimes using the original conditions may be easier, and sometimes using the alternative conditions may be easier. So you have to figure out which conditions to use for a problem, and you can only gain that thing by experience, right? So for a given problem, sometimes the original conditions may be easier to check, right? But sometimes, some other times, the alternative conditions may be easier. So, like in this case, for this question, the original conditions are easier, right? Okay, because this takes long, you know, as you can see. Okay. Any questions, guys? You okay? All right. The next one is the follow. The next one I'm going to do is the following. The extremal types theorem, which I talked about last week, does not always hold, right? I mean, what I mean by this is that there are examples where none of the three conditions will be satisfied, right? So So there are examples where none of the conditions 1, 2, or 3 will be satisfied. And I'm gonna give you just one example. One example is the following. Okay, let fx be equal to 1 minus 1 divided by log of x, where x is greater than e. E is the number e. I'm sure you know. Yeah. So clear. In this case, the first thing you need to do is to find the w of f. So you put fx equal to 1. So this becomes alright. This becomes this, yeah. And 0, alright. So log of x must be infinity, and x must be infinity too. So w of f is equal to plus infinity. Okay. All right. That's the first thing we need to do. The next thing we need to do is okay. The next thing we need to do is that we need to check the 3 conditions. So let's start with condition 1. Condition 1. So I'm gonna stick to the original conditions, not the alternative, but it will be the same. The results will be the same, right? So okay, this is condition 1, you should remember, all right? So this is equal to lim this is what you get. The 1 and the 1 will cancel, so this will be equal to the lim okay. Now can this be equal to ef minus x? You guys okay? Yes, no, right? There's no way it can be. So condition okay. Alright guys. Let me know if you have questions, guys. Right? So condition 1 fails to hold. So the next condition to check is condition 2. according to condition 2, WF must be equal to infinity, which is true in this case, and the limit is this. So this is the lim as t goes to infinity of 1 minus log of tx okay. You with me so far? Yeah, let me know if you have questions. Feel free, guys, to talk to me. So the ones cancel, so this becomes the limit as t goes to infinity of log of t divided by log of tx. Okay. Now this is the limit as t goes to infinity of log of t divided by log of t plus log of x. Right? Remember, log of tx you can write as log of t plus log of x. Now you should divide the top and the bottom. You should divide the top and the bottom by log of t. This is what you get, right? And as t goes to infinity, this guy goes to 0, right? So the limit is 1. So hence condition 2 fails. Guys, you remember what the limit should be. Well, what should be the limit if it is to hold? It should be, you remember, it should be x to the power minus alpha, right? You remember? Yeah. Come on, guys. So since the limit is 1, the condition 2 clearly fails, right? Okay. So condition 1 and condition 2 both do not hold. Now let's look at condition 3. Condition 3. Okay. WF is equal to infinity, right? So this implies that WF is not finite. So condition 3 fails, right? So all three conditions, So all three conditions fail to hold, and hence the extremal type theorem does not hold, right? Okay. So this is only one example, but there are many other examples where the extremal type theorem does not work. It's like in the central limit theorem, for example. I mean, when did you guys do the central limit theorem? In which course? Don't remember.
Probably.
Yeah. there are examples where the central limit theorem does not hold. You probably did. Did you do examples where central limit theorem doesn't hold? Oh, come on. Why you say don't know all the time? Come on. Anyway, and it's the same here. I mean, there are examples where a certain theorem doesn't hold, and this is just like in the CLT. There are examples for the ETT too, right, where the theorem does not hold. Right? Okay. All right. Any questions so far? Any questions? No? All right. I hope you like, I mean, okay, by the way, tomorrow we have an example class. Tomorrow we have an example class from 5 to 6. And for the example class, you will go through this problem sheet 1. You have a copy of this, right? Everybody. So try to go, I will not have time to go through all of them because there are 14. So I will only do like some of the questions. But before you come to the example class tomorrow, I would like you to try as many of the problems as you can. Okay? So I will go through the ones which are difficult, which you cannot solve. Right? So if you could do the easy ones, right? Then I will do the harder ones tomorrow. Is that okay, guys? Because I only have 1 hour. I can't go through all the problems in 1 hour, right? Okay. Right. So try to do as many problems as you can. Okay. All right. The next thing I'm going to talk about today is the following. So far, that's my. Right. So far what we said is that if condition 1 holds, then the limit is Gumbel, right? And if condition 2 holds, then the limit is Frechet. And if condition 3 holds, then the limit is Weibull. Okay? Okay, guys? So, but what we did not say is how to choose. Like, if you look at the extremal types theorem, it says that the limit of a scaled version of the sample maximum, right, approaches one of 3 distributions: Gumbel, Frechet, or Weibull. The scaling of the maximum, of the sample maximums, involves 2 constants, right, the constant an and the constant bn. So the next question we need to ask ourselves is how to choose an and bn. Remember, these two an and bn appear in the left-hand side of the limit, right? As n goes to infinity, it goes to one of the 3 distributions. So the question is, how do you choose an and bn, right? So to answer this question is as follows. If condition 1 is satisfied, right, then you choose an as this, and you choose bn as this, right? So these are the formulas for an and bn if condition 1 is satisfied. If condition 2 is satisfied, sorry, what am I saying? I mean, this is condition 2, I mean not 3. Condition 2 is satisfied, your an will be this, and your bn will be 0. Alright? And finally, if condition 3 is satisfied, we choose an as this, and your bn as alright. So these are, so depending on which of the three conditions is satisfied, these are the formulas for an and bn. Now here, when I wrote f inverse, I mean the inverse function of f. So I should make that clear. F inverse denotes the inverse function of f, right? I'm sure all of you guys know how to find the inverse of a function, right? So let's try to do some examples now. So I'm going to go through the 4 examples I did last week. Remember the 4 examples I did: the exponential, Pareto, uniform, and exponentiated Pareto, exponential, right? Alright guys, so let me start with example 1. Example 1, so example 1 is the following. Alright. Now we know which of the 3 conditions this satisfies. Can you remember? Which one? Come on, guys. For this one, which one was it satisfied? We just did it, guys. Come on. Yeah, so condition 1 holds. Yeah. So what we need to do is we need to find this one and this one, right? And do you remember we did this example last week? Condition 1 holds with gamma t equal to 1. So your an, what would your an be? An will be 1. Okay? And to find the bn, you need to set f of x equal to 1 minus 1 over n and solve for x. Alright, so your bn is equal to log of n. Alright, so your an is 1 and your Bn is log of n. Is that clear? Why? The reason is because, guys, these are the formulas you need to use, guys. This one and this one, right? And for that particular example, gamma of t, the function gamma of t is identically equal to 1. So your an is 1. And to find Bn, you need to set the CDF equal to 1 minus 1 over n, as I did over there, and solve for x in terms of n. And you get x equal to log of n. So your Bn is log of n. Is that clear, guys? You should. Okay. Good. Very good. If you're not sure, then this got me now. Alright, so the answer to the question is the following, that so what this implies is that nx, which is x plus log n Alright, so here what I've done, guys, is to put n equal to 1. So n times x is just x, and I put Bn equal to log of n. So it becomes x plus log of n, right? Approaches as intended to infinity. Huh? Is that clear, guys, or no? Yes? Alright. So that's example 1. Example 2. Let's do example 2 now. Example 2, remember, guys, is fx equal to right. Now, do you guys remember which condition was satisfied for this? 2, yeah. So condition 1, condition 2 holds. So in this example, we need to use these two formulas. So an equal to this and bn equal to 0. So to find an, you just simply set fx equal to this and solve for x in terms of n. So this becomes n equal to 1 and bn equal to 0. Alright. So by the ETT, by the extremal types theorem, on f, because bn is 0, this will be n times x, bn is 0, power n approaches as n goes to infinity to right. Okay, is that clear, guys? Because your alpha is 1, the power of x is minus 1. Okay. So in this case, in this example I have used this formula here, these two formulas, to find an and bn, right? That's because condition 2 was satisfied. Okay. All right. Next one, example 2. Next one, example 3. Now, for this example, you may remember which condition was satisfied. Was condition 3, yeah? Condition 3 was satisfied. So we will use these two formulas here, right, to find our an and bn. So before that, let's find the inverse function of f at this point. So I'm going to set f of x equal to 1 minus 1 over n, and this implies clearly that x equal to 1 minus 1 over n. So your inverse function, that is is equal to this. Okay, right? So your an according to this formula, your an will be 1 minus 1 over n, which is 1 over n, and your bn is equal to 1. Okay, do you follow what I'm doing? I'm using these two formulas to find the n and the bn. So hence, by the extremal types theorem, yeah, the f of x divided by n, that's your an, plus 1, this will approach the Weibull limit, which is this, if x is less than 0 and equal to 1 if x is greater than or equal to 0. Okay, alright, so this will approach this. Okay, alright guys, so this is example 3, right? Alright, so now the final one. After this I will take a break. I know some of you are getting. So this is example 3. Now example 4. After this we'll take. Example 4 was example 4 was this, yeah? And do you remember which condition was satisfied? It was condition 1 holds, right? So the formulas that we are going to use for this one this one and this one. Now, do you remember what the gamma t was? I think we did this last week. Do you remember? I think it must be in the notes from last week. Do you remember what the gamma t was? Just like 1. It was 1, yeah. Gamma t was 1. I mean, this is an example I did last week with gamma t is 1. So once again, your an is equal to 1, yeah? And to find bn, we need to find the inverse function. So we need to set and find x in terms of okay, and this implies that ef minus x is 1 minus, okay, so this implies your x is minus log of 1 minus n, sorry, power 1 over a here, right, like this, okay. So that's your BFN. So this implies that BFN is equal to minus log of 1 minus 1 over n to the power 1 over a, and like this. So by the extremal types theorems, right, your an is 1, so it will be f x plus bn, which is this one, right? So this approaches the Gumbel limit as n goes to infinity. Alright, sorry, can you see it? Yeah. So this is a little bit involved because we know an is equal to 1, but to solve bn we need to solve the equation. Alright. Okay. Are you okay, guys? So let's take a break now for 10 minutes, and if you have any questions you can ask me now too. Yeah. Right. Can I have the attendance sheet? Who has the attendance sheet? Okay. Thank you. Okay. You have questions? Maybe I made a mistake. AFT is this, right? Yeah, you're right. Yeah, it should be 1 over A. But it doesn't matter. It doesn't change the result. It's the same. Yeah. This also goes to 0, but then this also goes to 0, but then you have 1 minus 1 equals 0. So before you should. So So the whole thing will be set. I mean, in the bottom also you have. This is the example 4. So this goes to 0. Yeah, this goes to 1. Yeah, this goes to. This goes to 1 minus 1.
Yeah.
And this goes to. It's too small for me.
Seems like 7 minutes. Yeah, that seems like it's done with
The thing is, here, you see, you have,
I mean,
if t goes to infinity, then you have 1 minus 1.
you'll never know
Bottom
the
also you
answer.
have 1 minus 1.
You never know.
It's meaningless. So if you can't take it, that's why. You can't take it because you have 0, 0, 0. You're up. Oh,
Yeah.
You have a question?
Yes.
Come around. Hello.
Yeah. I mean, I just feel like it's only like I mean, the best food time is I won't come back to Sunday.
This is minus 1. So what they should be. So if this is 0, this is not being anything else.
Just what happens.
So carry on. If it's also infinity, minus 1. So that was your practice.
You don't want to.
I did 4 examples on this, so I should know how to. No, you got 1 week. You got 1 week to. How you?
Good, yeah, so over the weekend, I was taking a visit to the Queen's application for trying
就是整个是这样，对，然后阿尔法波那个角就是那个
I want to try again, I'm not trying again.
You got 1 week to go.
Yeah.
How about you? You okay?
I want to get it, I'm sure. If I try one more time, I'll go get it. As for these, you know, like, do we have to like, learn all forms, for example?
She go to the website, the course website.
Or is not
Yeah, it gives you like a list of comments. You've probably seen it already. If you haven't been, just go and see.
Next year, not 30, there will be a course next year. Yeah.
You guys have any questions? You have any questions?
Just because
You sure? Everything clear?
you're the one like pushing it away.
What about you guys? Do you have any questions? Sure.
got a type, you got a type.
No, you can't just cancel. You can't cancel
No,
one.
it's not round. It's
But
not
you
round.
have to explain why you can cancel. You have to explain.
I mean, it depends, like, really.
You have to explain why you can cancel. It's important. I mean, the step from this line to this line, you need to explain. You need to explain why you can cancel the one.
Yeah, I mean, no, but everywhere you go, like,
Have any questions?
all of those people are always trying don't know.
All right, guys. So can we begin now? We need. Hello, guys. Can we start again? Or you need more break? Hello, guys. I just been told that I made a mistake here. This should be 1 over A, guys. This is example 4 using the alternative conditions. This should be 1 divided by A, but it doesn't change the answer. So I'll leave it like that. Okay. So I'll leave it like that. It's not going to change anything. All right. Can we start again, please? right? The extremal type theorem says that there can be three possible limits for the sample maximum. All right? Right, but in practice, suppose, I mean, we are all mathematicians and we know how to check condition 1, condition 2, condition 3. We can do it, right, because we have mathematical knowledge. But somebody from, say, agriculture or biology or medicine or, they may not have the mathematical knowledge to actually check condition 1, 2, or 3, right? So given a data set, they may not be able to know like what distribution the sample maximum follows, right? I mean, they only know that there are three possible limits, but they wouldn't be able to identify the correct limit because they may not have the mathematical knowledge to check the conditions, right? So the question is, a practitioner, when I say practitioner, I mean in general, not a mathematician, like somebody working in a field, for example, right? All right. All right. So, I think around 10. Right, giving rise to the three limits, right? So one needs to know So I don't know. So the question is, instead of having three different limits, right? Can you have one formula, right, that combines the three limits into one formula, right? In that, if you have just one formula, anybody can use it because they don't need to check. If you have just one formula, you don't need to check any of the three conditions because you know that that's the formula combines the three into one, Right? So the question is, can the three limiting distributions, the Gumpel, the Frechet, and the Weibull, be combined into one formula? Right? So that's the question. So the answer to this question is yes. So the answer to this question is yes. They can be combined into one formula, and that formula is given by the following. So the answer to this question is yes.
Can't see.
Sorry. Can't see. You can't see?
Oh.
Can- So they can be combined into what is known as the generalized extreme value distribution, or the GEV distribution, right? Can you see it now or not?
No.
No?
Yeah.
You can?
Zero.
Come on, you should. Why do you guys you stay so straight? You can't see? Yes? Come on. All right. Okay. All right. Let me put this back. That's the problem. Yeah? Okay. Let me put this back. All right. Just finish writing it and let me know. I mean, you don't need to write. I will scan. I mean, had you seen my website for the scan notes? After every class, I scanned everything and put it on my website. So you don't need to copy anything. Okay. And I also give the podcast. Yeah. All right. So what I have said here, guys, is that the three limiting distributions, the Gumpel, the Frechet, and the Weibull, can be combined into one distribution, and that distribution is known as the GEV, or the Generalized Extreme Value Distribution. Right? Okay? And that's what I'm going to describe now. I don't know, there's something wrong with my pen. I can't get a good pen. I don't know why. All of a sudden it ran out of ink. Okay, let me see. Try to use this one. So in this page, I'm gonna describe the GEV distribution. GE So I'm going to, you can't see it now. So I'm going to describe what is known as the GEV distribution. Yeah. A random variable follows the GV distribution if its CDF is given by this formula. I know it looks complicated, but it's not really. Right? It's not really complicated. Must be positive. This is known as the location. It's known as the location parameter. And sigma, which is always positive, is known as the scale. Scale parameter. And psi, which is between, it's known as the shape. Parameter. Right? Alright, so this distribution has three parameters. The mu, which is the location parameter, sigma, the scale parameter, and psi is a shape parameter. Right? Okay, now all right, there are a few things I need to discuss. The first thing, all right, just give me a sec. The first thing is the notation. The notation I use to use to denote a GV random variable is as follows. This is the notation, right? And the second thing is the range or the domain. When I say domain, I mean the following here. I mean the domain. This is the domain, right? This is the domain of X for the GV distribution, right? So it's a set of all values of X which satisfies this function here, right? Okay, so let's see. The domain will be if psi is positive. If psi is positive, then it's the same as saying that right? So X is mu minus. So hence the domain is do you understand what I have done? See, I'm considering because remember psi is a parameter that can go from minus to plus infinity, right? Sorry, we should be there. Okay, psi is a parameter that can go from minus to plus infinity. So I considered the case where psi is positive, for instance. If psi is positive, then this condition here, this is the condition for the domain. It's the same as this condition, right? And this is the same as this condition, right? Okay, so the domain, so the domain of the distribution, of the GEV distribution, when psi is positive, is from this number to plus infinity. Okay, is that clear, guys? Right? Okay, now that's if psi is positive. Now if psi is, oh, running out of paper. Shit. If psi is negative, then the condition for the domain, which is this one, right, will be equivalent to x minus mu divided by sigma less than. Do you see why it changes to less than? What's the reason? It changes from greater than to less than. Why is that? Because you're dividing by a negative number. When you divide by a negative number, you need to change the sign, right? Okay, so this is the same as x less than hence the domain is right, hence the domain is this. Okay, now finally, if psi is 0, then right, because if psi is equal to 0, then this guy here is equal to 1, because this is 0, right, and 1 is always positive, right? So in this case, the domain is because this is true for all x, the domain must be from minus to plus infinity. Yeah. So you see the domains are different depending on. So just to summarize, the domain is if, all right, and the domain is right, and the domain is all right, guys. So this is a summary of the domain of GEV distribution, right? For the 3 cases, right? They are all different. Okay. All right. Now the next thing I'm going to talk about is the special cases, right? Okay. So let me put this here. Now I said, to start with, I said that the GV distribution, to start with, just a minute ago I told you that the GV distribution combines the three limits, the Gumbel, the Frechet, and the Weibull, into one form. But so far I did not explain why it combines the three limits into one form. So that's what I'm going to explain now, right? So right. So I'm gonna start with the case. I'm gonna start with the case that psi is positive. Right. So I'm gonna consider three cases. I will consider the case psi is positive, psi is negative, and psi equal to 0. And I will show you that in each of the three cases, the GV distributions corresponds to the one of the three limiting distributions we got earlier, the Gumbel, the Frechet, and the Weibull, right? So in this case, it's this one, okay? Now I'm going to write this as follows. Alright, I'm going to write this as follows. You see what I've done? I have written this guy here in this form. Yeah? Okay. Now let me I'm gonna call this equal to A and call this equal to B, right? So you can write this all right. And in this step, I'm going to call this, let me call this alpha, right? So you can write this okay. Now can you tell me what is A? Is A positive or negative? What's the sign of A? A is positive, yeah. So, but B can be anything. B can be any real number, right? So this is right? This, what you have here is the same as this one, right? So the same type of as this. Now, what is this distribution known as? This is the type 2 limit, right? Which is the threshold, right? So what we have shown is the following, that right? So what we have shown is that the threshold limiting distribution is the particular case of the GV distribution when psi is positive, right? Okay, is that clear, guys? Yes? No? Okay. Right, now the next one, so let me put this here. If it's not clear, just let me know, guys. I'm happy to go through again. So the next one I'm going to consider is where psi is negative. Right? So in this case, g of x is this. Now I'm going to write this. Give me a few seconds. I'm going to write it once. Okay, like that. Okay, I'm going to write it like this, but here you have to be careful because let me see, just a minute, give me a sec. Minus, okay, so I'm going to write it like I'm going to introduce a minus here. Right? You see what I've done? Alright, now let me call this A, and let me call this B. So you get this equal to exponential of minus ax plus b minus 1 over, right, in brackets. Okay, and finally let me call this equal to alpha. Alright, so this becomes exponential of minus x plus b to the power alpha. Right, and now this is of the same type as do you see what I've done? Do you guys follow what I've done? I mean, this is of the same type as the Weibull limit, because your A, this is your A, guys, right? The A is always positive. Remember, I defined A as minus psi divided by sigma, right? And psi is negative, so A is positive, right? Yeah? Okay, so this is of the same type as the Weibull limit. So what we have shown is the following. We have shown that the Weibull okay. So we have shown that the Weibull limiting distribution is the particular case of the GEV when psi is negative. So there is one more case left, which is psi equal to 0. Are you all clear about this? Because I want you to understand this clearly. Is there any point here which you did not understand? You sure? Are you guys okay? Okay, good. Yeah. All right. So the one final case, I don't know whether I have the time today, but the one final case I need to consider where psi is equal to 0. Okay, psi is equal to 0. In this case, right, because psi is equal to 0, you are taking the limit of the CDF of the GV as psi approaches 0. Right? Now, you can write this You ready to go home, guys? Alright, you can write this in this form, right? Okay. Now, in the next case, I'm going to make a substitution. Okay, I'm going to set m equal to 1 over psi. I'm going to make this substitution. So if psi goes to 0, what would m go to? M will go to infinity, right? So this will be the limit as m goes to infinity of Now, do you guys remember, do you know the limit of this? It's from your calculus courses. No? Come on, guys. Don't tell me you don't know. Right, this is where your math comes in. Oh shit, sorry. Sorry, man. It should have something like 1 minus z power as the limit of this as n goes to infinity. This may ring a bell. What is this equal to? E to the z. Right? So if you use this, guys, you will get you will get this to be, sorry, there is no need for a limit, but anyway, let's put this limit. This guy here will be e exponential of minus in brackets of exponential of x minus like this. So the answer is right, and this is of the same type. It's not easy, not difficult to see. It's the same type as right. It's the same type as this one. Do you recognize this, guys? What's this? This is the Gumbel distribution, right? So what we have shown is the following. That is, we have shown that the Gumbel limit is